Hello. In this video we will speak about Kfold cross-validation technique and how you could use it to optimize hyperparameters of your models. I will start with explaining you a classification method called K-nearest neighbors. It's a very simple and intuitive model. Next, I will tell you about Kfold cross-validation as a complement approach to a simple train test splitting. And finally, we will combine these things together and learn how could we optimize the hyperparameters of a KNN using a folding technique. So let's start with the K-nearest neighbors. Let's import some libraries, load some data. So this data contains information about height of a person, weight of a person, age of a person, and its sex. And we could plot it on a simple two-dimensional plot. It's a scatter plot. On x-axis we have a height, on y-axis we have a weight, and the color of the points indicates the sex of a person. So this is a simple classification tasks, and how could we solve it? So for example, for these two green points, for which we do know their heights and weight, but we don't know their sex, how could we determine their sex? So let's consider on this point as a small example. One reasonable thing to do is to look for some observations that are from our training set, which have about the same height and about the same weight as this green point. And this is what KNN method does. So basically it looks for k nearest neighbors to this green point, and the neighborhood could be defined in a different way, but typically you define it as a simple Euclidean distance between points. So we look for k nearest neighbors for this point. Let's say k equal to 3. In that case, the three closest points to these green points are these three gray points. Therefore, our classifier will decide that this green point is also a gray point, and therefore it's a male. And probably these gray points correspond to children. Okay, but what if we increase k? So the KNN method, its hyperparameter is k, is number of neighbors. So if we increase k, we will end up with a different model, and this model will give us a different prediction for this green point. So let's say we have k equal to 7, then amongst 7 closest points, let's say these closest points are these 3 red dots, these 3 gray, and this 1 red. So amongst these 7 closest points from the training set to this new test observation, we have 4 observations which are females and 3 observations which are males. So we need to derive that this observation is a female. So let's see another point again. If we want to classify this point, this green point, first we need to select a number of neighbors. Let's say again we have a model with k equal to 3, then 3 closest points are gray point, red point, and another gray point. Therefore we decide that this person is a male. Okay, so sklearn implements k nearest neighbors as a classification class, and we will go back to this class in just to this k neighbors classifier in just a couple of minutes. But first, let's see how Kfold cross-validation, what is Kfold cross-validation and how does this work. So the idea of Kfold cross-validation is instead of splitting the data into 2 parts, train part and the test part, and remember that we need to do that so we train our classifier, our prediction model, it could be a regressor, on a trained subset of a data, and then we assess the performance of this model on a test subset, on an unseen set of data. So instead of doing that, we could do the Kfold technique. And it's basically you split your data into K parts. In this example, we split the data into 5 parts. And we use 4 parts as a training fold. We train our classifier, our prediction model on this training fold. And then we predict observations from a validation fold or test fold and compute the performance of our model. Then we train another classifier, so like the classifier, the model with exactly the same hyperparameters, but we train it on a different subset of a data on this training fold, right? And again, we predict on a blue box on a unseen data. And we repeat this process as much times as we have number of folds. In this case, we repeat it 5 times. And we end up with 5 performances on a test folds. And we could average them to get an estimation of goodness of our model. So obviously this method is computationally harder than a simple train test splitting, because instead of training a single model on a training set, we train 5 different models with the same set of hyperparameters. So we train it 5 times instead of 1 time. But it turns out that this cross-validation technique gives us much better estimation of a model goodness. And we need to estimate model goodness to find a best value of a hyperparameters of a model. So for example, which value of K gives us overall better classification, K equal to 3 or K equal to 7. The way we do it, we use a cross-validation or we use a train test splitting. Okay, let's see an example of usage, this Kfold. So this is a small example. We have a vector of values from 0 to 19, and we want to split it into train part and a test part into 5 train folds into 5 test folds. So we repeat procedure 5 times. We invoke a method called split. Here we define a Kfold. It defines as folding with 5 folds. We almost always we should put a set parameter shuffle to true, and random state allows us it gives us a reproducibility. So if we run this multiple times, we will always end up with the same splits. And if I change it, let's say 7, then you see that the test splits are slightly different. And it's just for reproducibility purposes. So let's see. So this for loop goes like 5 times, and it gives us 5 set of indices. This is a train indices, indices of a train objects, and this is indices of test objects. And if you combine all these test indices, you will end up with the whole data, with the indices for the whole data, and all these subsets of test folds do not intersect. Okay, so how could we use this to compute the performance of a nearest neighbors classifier? And we will use an accuracy score as a performance metric. So our features are height, weight, and age of a person. Our target variable is a sex of a person. So what we do, we define a Kfold, then we create a vector to store scores, to store the accuracies on a test fold. We split our data into train and test fold. we train a classifier on a training part of the data, and then we predict the values on test data, and we store an accuracy score between our prediction and a true value, true sex of a person. So let's run it. X is not defined. So let's run it. So we could see that this is the shape of a training part of the data. This is the shape of a test part of the data. It's always the same. And the average performance is 67% test score. So test score contains accuracy scores for every single test fold. Okay, this is a perfectly fine way to do that. But since this kind of code is very common, sklearn implements a specific function called cross-val score. Basically, what it does, it do this for loop for you. So all thing you need to give it, you need to specify a classifier, then you need to specify your axis and y, and you could optionally provide it a specific Kfold, and then it will it will output you exactly the same vector of test accuracies. So what if you do not want these accuracies, and instead of accuracies you want to get the actual predictions on test folds? Then you could use a cross-val predict function. It does that. So it runs cross-validation. It splits your data into 5 parts. Basically, this cross-val predict is completely the same as running this training loop, but instead of saving accuracy scores, it saves y pred, right? And it gives you this. So it's a predictions for all 5 folds, and here it's also predictions for all 5 folds, but they are like arranged in a slightly different manner in the same order as they are presented in a y, in the original y. Okay, cool. So what's next? This is the performance of a k nearest neighbors classifier with k equal to 5. But what we actually want, we don't simply want the performance of a model with a specific value of a hyperparameter. What we want to find a model with an optimal set of hyperparameters. So instead of training a single classifier, what we typically do, we typically use either a grid search or a random search, and let's start with a grid search. So basically, grid search, the idea of a grid search is to run a model with a specific value of a hyperparameter. In the case of k nearest neighbor, we only have a single hyperparameter, the number of neighbors. So we set this parameter to some value. We run the model. We assess the performance of the model. Then we change the value of this hyperparameter. And again, we train a model. Again, we assess the quality of this model with a different value of a hyperparameter. And we repeat this procedure as many times as we want, as how many values of this hyperparameter we want to check. So we could do that manually, right? So we just need to add one additional loop here, right? So basically what we did, we add this loop, number of neighbors. So for every particular number, we train a classifier, we compute set of test scores, and then we average them, and we save them to the dictionary. And this dictionary, let's see this dictionary. So this dictionary, for every particular value of a number of neighbors, it saves the average accuracy on test folds. Okay? So we could do that manually, and again, it's perfectly fine to do that. But the problem is typically, like your typical model will contain not as one hyperparameter, but let's say 5 hyperparameters, so 10 hyperparameters. And what it means that instead of one additional loop, you need to use like 5 additional inner loops to loop over all these hyperparameters. So instead of doing that, sklearn implements, yeah, and again, it could be a little bit nicer using a crossval score, which is basically changing this part of a loop to a crossval score, but it could be even better. Using an sklearn grid search method. So what this grid search method do? You only need to specify the value of a hyperparameter, the range of different values of this hyperparameter, and then this grid search assess quality of models with this specific, with all possible values of this hyperparameter. So you passes in the classifier that you want to train, you passes the dictionary, the grid of the hyperparameter values, and again you could optionally pass a cross-validation class, and then you feed it. And I forgot to load it. So you end up the resulting grid search variable contains cross-validation results for all possible values of your hyperparameter. In this particular case, the all possible values that amongst them we were looking for a best parameter were all the neighbors between 3 and 22 with step 2. So here we could find all out of false accuracies for all the models, and it also contains a best estimator, which is a fitted best estimator with a best value of a hyperparameter, and the score for this classifier. So the best score was 0.75 accuracy, and the number of neighbors of a classifier is 11. So this is a good thing to do, and the grid search is a great technique, but there is another technique that allows you to do basically the same thing, look for best set of hyperparameters, and it's called a random search. And the difference between random search and the grid search is that instead of using uniform grid, which is like a grid search, right, we could pick values of a hyperparameters at random from some predefined like subset of boundaries, right? And how does it look like? So you need to define a subset where you will look for a best value of a hyperparameter. In this case, I said that I want to look for a best optimal value between 2 and 7t, and then the syntax is completely the same, and I want to search like 10 times. So the random search algorithm will 10 times it will pick a random value between 2 and 70, and then it run the performance assessment part, like this cross-validation and all this stuff. And again, we have a oh my bad. We have a best estimator, and we have a best score. So the value of a best estimator is different, and the best score is slightly worse than with a grid search, but really this model is slightly worse. But we actually check a much bigger subspace of possible parameters value, right? So we were looking between like 3 and 20, and here we were looking between 2 and 70, and we do it like in the same time, so only 10 iterations. And it might not look like too good because this best score is slightly worse than with a grid search. So with a grid search we get a 75 cross-validation accuracy, and here we only get a 73. But this random search technique, it really shines when we have more than one hyperparameter. So if instead of one hyperparameter we have, let's say, like 5, so then I don't know, maybe a metric. So with k nearest neighbors you could specify, so instead of Euclidean metric k neighbors classifier, we could use let's say L1 metric, right? So let's put p here, I don't know, 1 and 2. And maybe we could also use different leaf size. So I don't even know what is this parameter controlling. I don't know, maybe again we could use a random value from 10 to 50, and p, yeah, okay, let's remove p, and let's increase the number of iterations. Maybe it will give us a better thing. Okay, slightly better. So if you actually have like more than one hyperparameter, then this random search in exactly the same time, it will give you, it will cover much bigger subspace of hyperparameter values. Okay, so that's it for this video. Next video will be about building a classification model using a KNN.